Hello everyone, so in this video I'm going to show you some examples and solve some examples that confuses some of the students. Okay, so let's begin with a design amplifier, a design problem. You're given a bunch of resistors. Each one of them is greater than 2 kilo ohms, and all of these resistors, so that's basically the smallest resistor. You're not allowed to use no smaller than 2 kilo ohms, and a variable DC source and an input signal, and you want to design a difference amplifier, and I'm going to tell you what that difference amplifier, what's the meaning of a difference amplifier in a moment is, and such that it takes the input source, so this is the V input, okay, and the V input ranges between -5 and 5, and you want the output to be a scaled version from this value. You want it to range from 0 to 3 volts. Okay? So forget about everything, let's just understand this concept, and then we try to solve the problem using the given. And forget about this equation for the moment. Okay? So, what does that mean? It means that you have a -5 volts to a signal that ranges from -5 to 5, and the output should range from 0 to 3 volts. Which means that what you need, so that's the output and that's the input, you want to design something that produces an output given the input. And the output is nothing but a scaled version of the output. Okay? So, what are the values of A and B that does this conversion? From -5 to 5, converts it to 0 to 3. That's the question that I want to answer. Okay? So, let's have a look here. So what we're going to do, we're going to substitute by two numbers, because these are two constants, two variables that I need to find out what the values of. Okay, so I'm going to substitute by two numbers, get two equations and two unknowns, and solve. Okay, so when the V input is -5, the output is 0. So 0 equals A multiplied by -5 plus B. Okay, the second equation is when the V input is 5, the V output is 3. So 5 equals 3. Now let's again. V output is 3. Okay, and the V input is 5. 5A plus B. Okay, let's add these two equations. Okay, so 3 equals, adding them together, okay, so 3 equals 2B, which means that B equals 3 over 2. Okay, substitute by the B here, you get A equals 3 over 10, which is, roughly speaking, which is equal to 0.3. So the V output should be equals to 0.3 plus 3 over 2. Okay? Okay? So this is the input. Okay? So this is the equation that we should implement, that we need to implement. And this equation is going to convert the input signal or the input source which ranges from -5 to 5, it's going to convert it to an output that ranges from 0 to 3. Ideally, this is the equation that you need to implement. So whether you have this or you have that, then it is fine. Okay? So, what does this, that's basically a hint. Okay? And supposedly, this hint should match this equation. But because there's a mistake in this problem, so this hint does not match this equation. So if you're given a problem, like in an exam or so, and this problem happens to be, and you're given some kind of contradiction between these two results, then you can pick up any one of these two equations and try to implement it. So what you could work on, either work on this equation and try to implement this equation, or try to implement this equation, which means that you need to design a difference amplifier to implement this equation. So basically that hint was supposed to help you. Okay, was supposed to help you. Why? Because instead of you doing all these steps, I'm giving you this equation. But it turns out that this equation and this equation do not match. Okay? Whether you have this equation or you have this equation, this is sufficient for you to design the difference amplifier. You do not need this piece of information anymore. Okay? So what I'm going to do is that I'm going to pick up an equation of them and continue the problem with that. But before I do this, I'm going to give you another example on how to derive this equation again. So let's, if I, for instance, if I switch these two numbers, what would I get? So 0, 3, negative 5, 5. Okay, so that's the input and that's the output, although in this example it was the opposite. And what I need to do is that I need to find the corresponding equation to this. An equation similar to that one but corresponds to this value. Why am I doing this? Just for you to, just to illustrate to you how to solve, that's basically another example for you to solve the constants A and B using another example. If you were given this range instead of that one. So what I'm going to do, V in is this one, and V out is that one. V out equals A plus A multiplied by V in plus B. Okay, so when the V in is 0, V output is negative 5, so that's the value of the B. And when V in is 5, so V output equals 3, which is equal to 3A, which is unknown. What is V input? V input is 5 plus B. What is B? Negative 5. Okay, so then you do the math. A equals 8 over 5, which is roughly speaking 1.6. Okay, so the equation V output equals 1.6 V input minus 5. Okay, so clearly this equation is a third equation that implements this conversion. Converts from 0 to 3 to negative 5 and 5. Okay, so right now what I'm going to do is that I'm going to pick up this equation, okay, and try to implement the difference amplifier that implements this equation. Try to design a difference amplifier that implements this equation. So that is the equation that I'm going, V output equals 0.6 V input minus 5. Okay? So, what do I do in order to implement this equation? Let's first see what is a difference amplifier. A difference amplifier is an amplifier that has two inputs and four resistors. R2, R1, R4, R3. This is V2 and this is V1. Okay? So this is basically the difference amplifier. And this, you could check this in figure 2.16 in Cedra's book. Figure 2.16 in Cedra's book, Microelectronics. Microelectronic circuits. Okay, 7th edition. Okay, so that's the figure of the difference amplifier. V1 and V2, those are the inputs of the difference amplifier, and you're allowed, since it's a design problem, you're allowed to put anything on this V1, anything on this V2, and you're allowed to pick up any values for R1, R2, R3, R4, such that it does this conversion. Whenever the V input is fed to the system, it is scaled by 0.6, then we subtract negative 5 and get the V output. That's what we need to design. Okay, so how do we design this? Let's understand first what the value of V output is in terms of V1 and V2 and in terms of the four resistors. Okay, So V output. Of course, you're allowed to do some simplification. Some people might say, yeah, okay, since it's a design problem, I'm going to assume R1 over R2 equals R3 over R4. For instance, that would simplify the analysis a lot. However, I'm not going to assume this right now. Okay? I'm just going to solve it in a general case. V1. I'm going to call this Vx. Okay? V1 minus Vx over R1, which is the current passing here. Okay? Is the same as the current passing here, which is equal to Vx minus V output over R2. Okay? Why? That's okay. So that's the current is passing in this way. So the voltage is in the opposite direction, right? The current passes from the high voltage to the low voltage. And if I want to calculate the voltage difference, I take the high voltage minus the low voltage, which is V1 minus Vx, over R1. And then current passes from the high voltage to the low voltage, Vx minus V output over R2. Okay? So, V1 over R1 plus V output over R2 equals Vx 1 over R1 plus 1 over R2. And this is the first equation. Of course, if you know what the value of V output is in terms of V1 and V2, just put it if you memorize it, and just like mention where did you get it from the book, or it's mentioned in the book. Okay? But if not, then you need to derive it. Okay? So what about the second equation? This is Vx as well. Why? Because any op-amp, the V plus equals the V minus, and that's an ideal op-amp. Okay? So Vx equals voltage divider rule. The voltage over this resistor. Vx is basically the volt from this node to the ground. Okay, which is the same volt as the voltage over R4. So using the voltage divider rule, imagine that you have plus minus here, and this value is V2. Okay, that's the source. Okay, and let's do a voltage divider rule here. R4 over R3 plus R4 multiplied by V2. Okay, and let's substitute this here. So we get V1 over R1 plus V output over R2 equals R4 over R3 plus R4 multiplied by V2, 1 over R1, R2, R1 plus R2. Thus, the output, multiply everything by R2, then you get R4 over R3 plus R4, R1 plus R2 over R1, V2, and then you put this on the other side, V1, and then you have R2 over R1, because I multiplied the whole equation by R2. Okay, and that is the equation that we need to find the value of. Okay, we need to design using this equation. This equation describes how this circuit performs, and my duty is to put this equation on this form so that I can somehow find out the numbers that I want to find, which are the numbers of the components. Okay, so actually what I'm going to do is that I'm going to solve using the method of comparison of coefficients. Okay, I'm going to compare the coefficients together, and I'm going to choose the numbers for R4, R1, R3, and R2, and V2 and V1, so that I can implement this equation. Okay, obviously, what do I have? I have a variable DC source. What is a variable DC source? A variable DC source is a DC source, but it's variable. You're allowed to change its value. It could be -1, -2, -3, 4, 5, +6, +7, any value. it's a variable, but once you fix it, it's not. So that's the difference between the variable DC source and the AC source, okay, which is the V input. The variable DC source is once you fix it, you're not allowed to change it during the operation of the circuit, okay. Otherwise, it's going to change the whole performance of the system, okay. While the V input, while the AC source is a source that is already changing, and you do not have any control over it. And in our example, it is given as this value, or perhaps it's given as this value. So it's in general, it's a value. Whatever this value is, it's going to change. I do not have any control over it, unlike the variable DC source, which is the one that I have control over it. So if you look here, I need to. These are the voltages, okay, V1 and V2. I want to put something in V2, something else in V1, in order to implement this equation. As you can see, I cannot put, so V2 here is multiplied by a positive number, while V1 is multiplied by a negative number. Okay? And my duty here is to let V in to be multiplied by a positive number. So obviously, I cannot choose V1 to be V input. That's impossible. Why? Because if you choose V1, if you put V input on the source V1, then you definitely are going to get a multiplication by a negative, although V input is multiplied by a positive number. Okay? So, what I'm going to do is that I'm going to set V2 equals V input. Just by inspection. Okay? You compare these two equations together. I'm going to set V2 equals V input. What about V1? I'm going to set V1 to a value such that this whole is equal to 5. This whole number is equal to 5. So that's not V input anymore. Okay? And I'm going to set this to be 5. Okay? And then you're allowed to choose to do whatever conversion that whatever assumption that you have. Right now I've set V2 equals V input, V1 equals 5 equals multiplied by R2 over R1 equals 5 volts. Okay? So that's the value that will control the value of the DC source. I'm going to solve for V1 in a moment. Okay? And right now what I'm going to do is that I'm going to choose the values of R2, R1, R3 and R4 such that this whole thing becomes equal to that. Okay? There are two options actually, two obvious options. The first one is, let's solve it here. The first one is choose R2 over R1 equals R4 over R3. Okay, which is basically this equation. Okay, so right now I haven't really used this equation yet. Okay, I'm going to use to solve it using this equation. So if I put this here, so I get V output equals, if you do the math, you'll get V output equals R2 over R1, V input minus R2 over R1, V1. Okay, obviously this value is 5, so it maps to this equation, so you need this to be equal to 0.6. 0.6 equals R2 over R1. Okay, which means that 0.6, what is the, okay, so since the smallest of them, so which one is smaller? R2 is smaller or R1 is smaller? Actually R2 is smaller because this number is less than 1. This number, since 0.6 is less than 1, then this R2 is smaller. And you want the smaller value to be 2 kilo ohms. Okay, so R2 equals 2 kilo ohms, which means that R1 equals 2 over 0.6, which is roughly speaking, which is, you can do the math, it's, let's see, 6 over, so that's 10, 20, 20 over 6, 10 over 3, roughly speaking 3.3 kilo ohms. Okay, which this is equal to R3, and this is equal to R4, by assumption. Okay, so right now I've solved this problem. Okay, and thus you can get V1 equals to, V1 equals to 5 over R2 over R1, which is 0.6. Okay, and this becomes multiplied by 5 over 2, so 10, so 1.3 times 5, roughly speaking, equals 6 volts, roughly speaking, or 7, close to 7 volts. You can do the math, okay? You can do 10, 50, 50.5 over 3 equals 8, 25 over 3 equals 8, roughly speaking. 23 volts. Okay, so that's the first method. Or you could choose to set R2 over R1. Okay, so that's the first method. The second method is I'm going to choose to set R2 over R1 equals 1. Okay, thus V1 equals 5 volts. Okay, so V1 equals 5 volts. R2 over R1 equals 1, so they are equal, which means that this value is going to be 2. Okay, so right now, remember that the first method is to set this assumption. The second method says that, no, I'm not going to set this assumption, but otherwise I'm going to say R2 over R1 equals 1. So that's the assumption that I'm going to follow. Okay, in that case, V output equals 2 R4 over R1 plus R3 plus R4. Okay, because this is going to give you a 2. V input minus 5. Okay, and thus you should be able to set this to 0.6 and find the values of R4 and R3. Okay, so that is the way that we solve these kinds of problems. So even if you're given such a contradiction, pick any one of them and move forward with the problem. Okay, and remember that till now I did not, even in the design, I did not make use. I made use only of this equation. I did not make use of this kind of numbers and ranges so that I can solve for the values of R1, R2, R3, and R4. I did not need it. All what I need is this equation. Okay? Can we use these numbers? Yes, you can. If you're going to use them, then you need to make sure that the equation that you're going to solve for matches these numbers. But actually, it does not. Okay, but in general, if you're going, for example, if I give, instead of giving you this equation, I give you this equation. And in that case, you're allowed, instead of doing the method of comparison of coefficients, you're allowed to use these numbers. But I do not recommend that. I highly recommend the method of coefficients. Okay? So this is the first problem that I'm going to solve. Okay? Okay, so in the second problem, I'm going to solve a problem for the diodes. And what is required from this problem is that you're given a diode, a circuit that has a diode and other components, and you're required to find V output versus V input. What is the effect of this diode on V output versus V input curve? So basically you want to plot V output on the y-axis versus V input. When you sweep V input from negative infinity to positive infinity, and see what the value of V output is. And it is defined that V output is the voltage over these two components, the battery and the diode. Okay? So let's remember the operation of the diode. That's a diode, okay? And the way that I memorize it is that this is P and this is N. So as if this is telling me this is a positive and this is negative. Which means that Vp, if it's larger than Vn, the positive is larger than the negative, then the diode is a short circuit. Okay? Then the diode is on, is conducting. Otherwise it is off. So that's the way that I memorize it. Okay? Vp and Vn. Okay? Of course, you need to know that that is the diode. I'm going to flip it. Okay? So this is basically, that's the cathode and this is the anode. That's the cathode direction and that's the anode. And if you want to memorize it, that's letter K, which means that this is cathode. That's just a method of memorizing or finding out which one is the cathode and which one is the anode. Anyways, that's a separate story. So Vp and Vn. So you need to find when Vp is larger than Vn and put a short circuit. Okay? So, or perhaps you might put a battery. Okay? You might put a battery. And the battery is going to be Vp is going to be plus and minus according to this scheme. Okay, so forget about this at the moment. Okay? So, and this is the constant voltage drop. And that's more general, so I'm going to solve with the constant voltage drop model. Okay? So, I'm going to put V in is very, very small. Smaller than the zero. So let's say the input is negative infinity. Okay? Which means that this voltage is much lower than that voltage. Okay? Which means that this voltage is much lower than this voltage. So this is negative with respect to that. So which means that Vp is higher than Vn. So it's on. When we have a negative voltage, this voltage is small, so this voltage is larger than this, so we have an on circuit. So let's draw it, plus minus, and V input is less than 0. Okay, plus minus, and we have here battery, minus plus. Okay, so that is 0.7. Why did I put the plus down? Because the plus should map with this triangle. Okay, 2 volts, 1 kilo ohms. Okay, and the required is this V output. Obviously, this output voltage is constant, it doesn't change, there is no resistor here, so the output voltage is constant. How do I calculate the output voltage? Let's do a KVL in this circuit. Well, that might confuse you. Okay? I'm going to say the systematic way and then say the KVL way. Okay, so what is the voltage of the output? The output starts from down to top, from here to here, from the negative to the positive. Okay, so I'm going to look at this node and move forward till the top and see what is the value of the voltage at that node compared to this node. So that's assume that this is the 0. Okay, when I move top, I pass by a voltage source, and the value of the voltage source is 0.7, pointing down. Okay, so this node compared to that node, since it's pointing down, so that's negative 0.7. Okay, again, from this node to that node, it is negative 0.7. Why negative 0.7? Because the voltage source points down, opposite the direction of motion. I'm moving from down to top. Okay, so right now this is negative 0.7. So when I move to above again, what do I see? I see a voltage of 2 volts, which means it's helping me. It's in the same direction of motion. So that is, this node is negative 0.7 plus 2. Because why plus 2? Because it is helping the direction of motion. Okay, that is the way that I solved. If you have any other way, do it the way that you like it. Okay, which is equal to 1.3 volts. Okay, so V output is 1.3, irrelevant of what the value of V input is, as long as V input is very small. Okay. If you want to solve it using the KVL, then you take this loop. Okay, this loop is V output. Okay, which is equal to these voltages, 2 minus 0.7, which is 1.3 volts. Why 2 minus 0.7? Because the 2 is in the same direction, so that's why I put it as a positive 2, and this is as a negative 0.7. So that is the value of the output. Okay, so the V output is always constant with respect whenever the V input is very small. So when do you expect that the V output, that this diode is going to switch from on to off? plus minus, that's the resistor, plus minus, that is when the diode is going to be off. When is it going to be off? When this Vn is larger than Vp by 0.7. Okay? Is larger than Vp. So the difference basically, so that's, okay, Vn. Okay, so in order for this to happen, Vp has to be smaller than, okay, for the on, Vp minus Vn has to be larger than 0.7. Okay, so this is 0.7. Okay, so that's for the constant voltage drop model. If you have a constant voltage, if you do not have a constant voltage drop model, then this 0.7 becomes a 0, which is the ideal case. Okay, so when Vp minus Vn is smaller than the 0.7, then it becomes off. Okay, so Vn plus 0.7 is greater than Vp. This is the same as this equation. Okay? So when is this value greater? So I need to find a way to map this circuit to this equation. I want Vn plus 0.7 to be equal to be greater than Vp. Okay? What is the value of Vn? That is the value of Vn. What is the value of Vp? This is the value of Vp. Okay? So the value, let's do a nodal analysis. Take the ground here. Okay? This is Vn, and this is 2 volts. And since there is no current passing here, then I do not expect to have any voltage across the resistor. Okay? So let's take this node and see what the value of Vn is. Vn is Vin minus 2 volts. Minus 2 volts plus 0.7 has to be larger than Vp, which is equal to 0. Why equal to 0? Because I'm taking this as the reference. Okay, so Vn is greater than 1.3 volts. So that is the threshold. Okay, so that's, in my opinion, that's the easiest way, is to find it using the KVL. Okay, so in that case, what is the value of V output? V output equals plus minus. Okay, so I'm going to take it here again. So this is V output as per this equation, as per this diagram. Okay, so that's the V output. The V output here is equal to V input. Why? Because I guarantee that there is no current passing through the resistor, which means that V output is equal to V input. Okay, so since we have solved this problem, V output equals V input, and V output equals 1.3, and the threshold is at 1.3. So that's 1.3. Okay. Before 1.3, V output was equal to 1.3. So this is 1.3. After 1.3, V output equals V input. So that's a straight line passing by the 0. Slope equals 1. Okay? And this becomes the final graph. Okay? So the problem that confuses you is two things here. The first one is that V output is not the voltage on the diode, and the second one is that how to decide whether V input, whether the diode is on and off. Okay, so right now take a notice whenever you are given a diagram. Take a notice of where the V output is, and do not change it, because if you change it, you'll get confused and you'll find another voltage and another output voltage other than the one that is required. Okay, so do not change this value, the location of this V output voltage. Okay, what about for determining the diode, whether it's on or off? You have to notice that Vp has to be larger than Vn. Vp has to be larger than Vn. And if it was a constant voltage model, then it has to be larger by 0.7. Okay, so the difference here has to be larger than 0.7 volts. Okay, so when it is smaller than that, which means that this voltage is very small, then you guarantee that this diode is going to be off, an off diode. Okay. Okay. So for the third problem, you're given a transistor, a MOSFET transistor that is connected in this way. Okay, and I'm giving you that ID is equal to 0.3 is equal to 37.5 microamperes. Okay, what I'm asking the power consumed in this circuit. Power consumed. So whenever I ask you about the power consumed, P equals volt multiplied by current, or equals to V squared over R, or equals to I squared multiplied by R. You're allowed to use any of these formulas, the one that suits your case. Okay, but whenever I ask about the power consumed, I need the power consumed by the whole circuit. So in other words, how much power is consumed from these batteries? Okay, so not just the power consumed in this resistor, nor in this, nor in this, nor in the transistor, but the power consumed in the entire circuit. Okay, so it's totally wrong to calculate the power by this resistor, which is voltage difference over voltage difference squared over R. Okay, and it is totally wrong to calculate and add it to the power consumed by these two resistors. There is, in fact, there is some power consumed by the transistor, and that's why you're not allowed to choose only the resistors and see the power consumption in the resistors only. No, there is some power consumed in the transistor, and you need to take account of that. But instead of calculating the power in the transistor, what I'm going to do is that I'm going to calculate the whole power consumed from the battery, and it is equal to the power consumed in the components. Okay, so the power consumed in the battery is 5 volts, okay, multiplied by the current ID, 37.5, okay, plus the voltage over these two resistors. Voltage squared, which is 5 squared, over these two resistors, which is 10 plus 40. And that is in kilo. Okay? So what I've done is that I've calculated, so these are basically two batteries. Okay? One of them supplies the current ID, and the other one supplies some current that passes through these two resistors. The current that passes through these two resistors will consume some power, and the current passing through this resistor and the transistor will consume some other power. Okay, and that is the value of the power in the resistor RD plus MOSFET, and that is the power passing through 40 plus 10. The 40 plus the 10K. Okay, if you want to calculate the current passing here, you can, I equals V over R, which is 5 over 50, which is 0.1 milliampere. Okay, and that's in micro. Okay, and then multiply the current 0.1 by the 5. You can do this or you can calculate it this way. Okay, hope this helps, and if you have any questions, please let me know.